Welcome to the deep dive. It's great to have you with us today.
Yeah, really glad you could join us.
Since we know you're constantly juggling different technical frameworks, research papers, and deep dives of your own, we thought you'd appreciate how this specific piece of internet history mirrors a much broader strategy for managing information overload.
It really does. It's
Yeah.
a fantastic example.
Right. So for this deep dive, we're embarking on a mission to extract the most fascinating practical nuggets of knowledge from a source that is incredibly specific, beautifully mundane, and just wonderfully relatable.
I love how you phrase that because it really is all of those things.
Today, our focus is on a single blog post. But, not just any blog post. This is a dispatch from an author who affectionately describes himself as an old software plumber.
Which is such a great moniker.
It really sets the tone. Specifically, we're looking at a post from qianmeng.org, published on March 9th, 2026. It's titled, Notes on Haskell Programming, Part 77. Optimizing file reads in Haskell the right way.
Part 77. Just think about that for a second.
I know, right? And our goal today is to show you why this tiny slice of the internet holds some massive lessons for how we handle our code, our workflows, and really our mental bandwidth.
It is fantastic to be here unpacking this with you. When we look at highly technical blogs, it is incredibly easy to get lost in the syntax and the raw code blocks.
Oh, absolutely. The eyes just glaze over.
Right. We often forget that there's a human being on the other side of the screen wrestling with these systems late at night. But this source gives us a remarkably detailed portrait of a tinkerer at work.
Mm-hmm.
We aren't just looking at a few lines of Haskell refactoring. We are observing the meticulous, disciplined process of problem solving. It's about the rigor of identifying a system inefficiency, patching it, and then documenting that fix.
Documenting it for himself, mostly?
Yes, so the author and anyone else crawling the web for a solution can learn from it down the line.
Okay, let's unpack this. Because before we get into the actual Haskell optimization, we have to look at the environment this post lives in. To truly appreciate Part 77, you have to understand the sheer scale of what Qianmeng has built here.
The scale is honestly hard to wrap your head around at first glance.
It is. He has been documenting his work on this blog since 2011. And when I say documenting, I mean a level of dedication that is, frankly, staggering.
It's not a casual hobby.
No, it's a daily journal of tinkering. Just looking at the stats he provides in the source, in the year 2024 alone, there were 732 posts.
2 a day.
Basically, yeah. In 2025, another 730 posts. And by early March of 2026, when this post was published, he had already crossed over 200 posts for the year.
The volume alone is an impressive feat of discipline. I mean, writing 2 posts a day, every single day, for years on end requires a serious system.
You definitely don't just wait for inspiration to strike to hit those numbers.
Exactly. You do not maintain that kind of output by waiting around. You maintain it by treating documentation as an integral part of the work itself. It's not an afterthought. It's the final step of the task.
And the volume is one thing, but the sheer breadth of topics is what really catches your eye. You scroll through the archives, and right alongside these deep technical notes on Go, Rust, and Elixir programming.
You find the garden stuff.
Yes, you find the most wonderfully quirky, specific life updates. There are detailed notes on propagating bougainvillea, dealing with leggy seedlings in a garden.
I love the leggy seedlings entry.
And there's a whole entry dedicated to the gelatinous pear.
Which just sounds so intriguing.
Right. There are meticulous betta spawn logs, notes on adapting specific water parameters for fish keeping. He's got notes on dieting, specifically investigating something called the truth about icosa.
Right alongside observations on typesetting, meditation, playing the guitar.
It is the ultimate portrait of a lifelong learner who just completely refuses to be pigeonholed into a single discipline.
What's fascinating here is that if you look closely at the source, it's not just a random assortment of hobbies. It might look scattered at first, but there is a deeply unifying thread here.
Oh, what do you see as the thread?
It's a profound, abiding commitment to free libre and open source software, or FLAUDAS.
Ah, yeah, that makes total sense.
This entire journal is a living, breathing testament to the open source ethos. The author isn't just taking from the community, he's constantly giving back by documenting every small victory and every minor bug fix.
Leaving a trail of breadcrumbs for the next person.
Precisely. And he puts his tangible support behind the organizations that protect this kind of open ecosystem. The blog explicitly lists the groups he supports.
Right, I saw that list.
He mentions the Electronic Frontier Foundation, the Free Software Foundation, the Software Freedom Conservancy, the Tor Project, and Wikipedia.
That's a solid lineup of open web defenders.
It paints a picture of someone who views knowledge not as a proprietary asset to be hoarded, but as infrastructure to be maintained and shared continuously.
That infrastructure mindset really shines through in his tone, too. He has this very pragmatic, grounded attitude. He even includes standard disclaimers on his site.
Right, covering his base.
Exactly, explicitly stating that all opinions are his own, they don't represent his employers, the content is for informational purposes only, and he accepts no liability for any loss or damage.
Very standard, but very necessary.
It's a very clear, I am just sharing my notes, use them at your own risk vibe. It fits perfectly with that old software plumber persona. He's down in the basement fixing the pipes and letting you watch the process.
And that metaphor is perfect for what we're about to discuss.
Exactly, which brings us perfectly to the specific plumbing issue he is fixing in part 77 of his notes on Haskell. Let's look at the actual code he wrote to patch it.
Let's dive into it.
He's doing some refactoring and has a realization about how his program handles file reads. He notes that reading an entire large file directly into memory is suboptimal.
To put it mildly.
Right. But more critically, he realizes his code lacks proper resource management for the open file.
That is the absolute core of the issue. As you know, whenever you open a file, the operating system assigns a file descriptor to that process.
Like a little ID tag for the open file.
Exactly. The problem is that file descriptors are a finite system resource. The OS allocates a table for them, and there is a hard limit on how many can be opened simultaneously.
You can't just open files forever.
You cannot. What the author realized was that his Haskell code was acquiring this file descriptor, but it wasn't reliably releasing it back to the operating system. In system architecture, you are looking at a classic resource leak.
But wait, let me play devil's advocate here. If he's reading the file, wouldn't the system naturally close it when the garbage collector runs? Or at least when it hits the end of the document? Why is an explicit close such a massive priority here?
That is a great question, and it gets to the heart of how different programming languages handle memory versus system resources.
Okay, lay it on me.
In a language with garbage collection, like Haskell, memory management is automated. When an object is no longer referenced, the garbage collector eventually sweeps it away and frees the memory.
Right, you don't have to manually free things like in C.
Exactly. However, file descriptors are not memory. They are operating system resources. The garbage selector does not know or care about the OS file descriptor table.
Ah, so it cleans the heap but leaves the OS hanging.
Precisely. Furthermore, Haskell is a lazily evaluated language. It tries to avoid doing work until the absolute last moment.
Lazy evaluation, right?
So if you tell Haskell to read a file, it might not actually read the contents right away. It might just build a an unevaluated expression representing the read operation.
Meaning it's just a promise to read it later.
Yes. And if you force the evaluation of a massive file all at once, you blow up the heap. But even if you manage the memory correctly, if the program crashes or throws an exception halfway through reading, the function that was supposed to close the file never gets called.
Right, the execution halts, the program panics, and the descriptor is just left dangling.
Precisely. The file descriptor stays open. If this happens once or twice, you might not notice. But if this code is running in a loop or operating as a daemon, parsing log files constantly,
Just constantly acquiring descriptors and never releasing them.
yes, the system's resources slowly drain away, and the text explicitly points out the system-level consequence of this. Eventually, the operating system intervenes and throws a too many open files error.
Game over.
The process is denied any further file access, and the whole system can grind to a halt.
So swallowing the whole file is a bad idea, and leaving the file descriptor open is a ticking time bomb. How exactly does he fix the plumbing here?
He implements a highly specific two-part optimization. First, he tackles the memory issue by changing how the data is ingested.
Okay.
Instead of pulling the entire file content into memory at once, he limits his read. He uses a function called BString.hGet to read only the first 1024 bytes of the file.
Here's where it gets really interesting. For those who haven't tinkered with Haskell recently, could you break down what BString is doing differently here compared to a standard file read? And why exactly 124 bytes?
Absolutely. BString refers to a byte string. In Haskell, a standard string is implemented as a list of characters.
Which sounds fine in theory.
It does, but because of how lists work in Haskell, this is incredibly memory intensive. Each character has a lot of overhead.
Got it.
A byte string, on the other hand, is a much lower level, highly efficient array of raw bytes. It maps much closer to how the machine actually handles data.
Oh, so it's stripping away all that Haskell list overhead.
Exactly. By using BString.hGet and passing it the size of 1024, he's instructing the program to take a small, manageable 1 kilobyte SIP of the data, process it as a raw byte array, and then move on.
A 1 kilobyte SIP. I like that.
It completely bypasses the memory bloat of standard strings and avoids pulling the entire file into the heap.
That makes perfect sense for the memory overhead. It's a localized, efficient chunk. But limiting the read to 1024 bytes doesn't solve the file descriptor leak if the program throws an exception during that read. The descriptor is still vulnerable.
Exactly right. And that is where the second part of his optimization comes in. To solve the resource leak, he switches his code to use a standard library tool called withFile.
withFile. Okay.
This is where the underlying philosophy of Haskell really shines. By wrapping his file operation inside with withFile, he guarantees that the file is closed properly afterward. Absolutely, regardless of what happens during the read process.
How does withFile guarantee that? Under the hood, what is it actually doing differently than just a standard open file and close file command sequence?
If we connect this to the bigger picture, the author notes that while drafting this very blog post, he learned the specific terminology for this pattern in the language. He learned that withFile is what's known in Haskell as a bracket function.
A bracket function.
Yes. And a bracket function is defined by an unbreakable three-step pattern designed specifically to manage stateful resources in a purely functional environment.
So what's step one?
First, you have the acquire step. In this case, withFile asks the operating system to open the file and return the file descriptor.
Okay, so it successfully grabs the descriptor. What is step two?
Step two is the use phase. This is where withFile hands the open file descriptor over to whatever computation you actually want to perform. In his case, that's the BString.hGet function, reading those 124 bytes.
Right, the 1 kilobyte SIP.
Exactly. Finally, step three is the release phase. This is where the file is explicitly closed and the descriptor is returned to the OS table.
I see. But earlier we talked about how an exception during the use phase bypasses the closing of the file. How does a bracket function prevent an exception from skipping step three?
Because the bracket function structuralizes the error handling. It leverages Haskell's exception control architecture.
How?
If an exception is thrown during the use phase, the bracket function catches it, immediately suspends it, automatically executes the release phase to close the file, and only then rethrows the exception so the rest of the program can handle the crash.
Wow. So it forces the cleanup before it lets the panic propagate?
It forms an ironclad guarantee. If you acquire the resource, the release phase will execute come hell or high water.
It's literally like putting a structural bracket around the vulnerable code. The system fundamentally says, I will not let you acquire this resource unless I am absolutely guaranteed to execute the release function later.
That's the perfect way to visualize it.
It completely removes the cognitive burden of remembering to close the file from the programmer's shoulders. The language handles the cleanup automatically, safely shutting the valve and returning the system to a stable state.
Totally eliminating the risk of that too many open files error.
Right. It is clean, responsible engineering.
And it represents a profound shift from imperative programming. In an imperative language, like C or early Java, you are essentially micromanaging the computer.
Doing everything by hand.
You have to explicitly type, open the file, read the file, and please check for errors, and do not forget to close the file in a finally block. You're manually managing the control flow.
That's exhausting just thinking about it.
The bracket function is a declarative approach. It structuralizes safety. It acknowledges that systems are chaotic, things will go wrong, databases will disconnect, and errors will happen during the use phase.
Because they always do.
Always. But by wrapping the operation in this acquire and release pattern, it ensures that a localized failure does not cascade into a system-wide resource leak. It isolates the damage and keeps the environment clean.
So what does this all mean? Since we know you, the listener, are constantly acquiring new information, synthesizing research, and managing your own complex projects, the immediate technical takeaway here is clear.
Leverage bracket functions, manage your system calls, and avoid memory bloat by reading data in efficient chunks.
Exactly. But there is a much broader takeaway here about how we operate as professionals and continuous learners. Think about the profile of this author.
Qian Meng.
Right. Here is a person who is constantly acquiring new, highly disparate information. One day he's analyzing Wi-Fi 7 MediaTek routers. The next day he's researching the flame dwarf cultivar for his gardening notes.
The next he's dealing with a betta fish spawn.
And then he is right back to optimizing byte reads in Haskell. He is managing a massive influx of data, but he doesn't let it overwhelm him or crash his system. He processes it, writes it down, publishes it, and moves on.
This raises an important question, and it brings us to a fascinating meta layer of the source material. What we are really looking at in this blog is a masterclass in the discipline of lifelong learning.
How do you mean?
The author's approach to his daily journal is very much like a bracket function for his own brain.
Oh, I like where this is going.
He constantly initiates the acquire phase by encountering a problem, like a resource leak in his Haskell code, or a leggy seedling in his garden that isn't thriving.
That's step one.
He enters the use phase by tinkering, reading documentation, experimenting with BString, and finding a solution.
Step two.
And then, crucially, he executes the release phase. He writes it down in his daily journal, categorizes it, adds his disclaimers, and publishes it to the open web.
Yes.
By systematically documenting it, he offloads it from his own active working memory. He explicitly closes the file descriptor in his mind.
That is exactly the parallel. He
Yeah.
isn't walking around trying to hold on to the exact syntax for BString.hGet or the precise pH water parameters for his fish tanks in his working memory all the time.
No one could.
Right. He has systematically externalized his knowledge. Look at the sheer volume of his output again, over 700 posts a year. When you are writing at that cadence, you cannot be precious about it.
You can't let perfect be the enemy of good.
You just have to document the finding, push the code, and release it. And in doing so, he has built this incredible searchable archive, a digital garden that goes all the way back to 2011.
It was remarkable.
The blog shows he has his Now page, his This Week in Review, his research papers to read, his Perl Weekly challenges. He has structured his curiosity in a way that is incredibly productive, highly visible to the floss community, and most importantly, entirely sustainable.
Sustainability is the operative word. We live in an era of constant, frictionless information acquisition. We're always opening new browser tabs, downloading new white papers, subscribing to new feeds.
Always in the acquire phase.
We are brilliant at the acquire phase.
Yeah.
We're relatively competent at the use phase, where we skim the material or apply it to a meeting. But as knowledge workers, we are often terrible at the release phase.
Oh, guilty as charged?
We leave all these mental loops open. We leave tabs sitting in our browsers for weeks, creating cognitive overhead.
Just draining system resources.
What the old software plumber teaches us is that you have to close the loop. You have to write down the note, file the journal entry, push the commit, or simply decide you're done with the topic and actively release the resource. Otherwise, you end up with debilitating resource leaks in your own focus and attention.
When we trace the arc of this deep dive today, we started with a highly technical, seemingly microscopic system problem, a Haskell program that was loading too much data into memory at once and failing to release its system descriptors.
A classic plumbing issue.
Right. We saw how the author optimized the process by intelligently sipping the data, reading only 124 bytes with BString.hGet, and utilizing withFile to manage the file descriptor lifecycle.
We unpack the elegant logic of the bracket function acquire, use, and release,
which leverages Haskell's exception handling to guarantee that an operating system resource is always returned, preventing the dreaded too many open files crash.
And by zooming out from that microscopic code fix, we discovered the much larger ecosystem of Optimising.org. We got a glimpse into the methodology of a dedicated open-source tinkerer.
Someone who applies the exact same diligent, problem-solving mindset to everything from low-level software architecture to cultivating bougainvillea and logging betta fish spawns.
Ultimately, the overarching value of this source material isn't just about how to write better functional code. It's about how to build a resilient system for interacting with a complex world.
Exactly.
It demonstrates that whether you are tinkering with Wi-Fi 7 protocols, trying to maximize plant propagation, or fixing a resource leak in a script, the disciplined process of documenting the acquire, use, and release of knowledge is invaluable.
It's the only way to keep moving forward.
It is a reminder that while the work of learning is never truly finished, each individual lesson needs to be properly closed and filed away so that we have the mental bandwidth to tackle the next complex system tomorrow.
And that brings us to a final thought we want to leave you with today. We have talked extensively about how Haskell uses a bracket function to guarantee the safe release of a digital resource, ensuring the operating system isn't overloaded by dangling file descriptors.
The structural bracket.
Right, but think about your own daily habits and workflows. In an age where we are constantly bombarded by raw data, rapid-fire communications, and endless algorithmic feeds, We're continuously opening new mental files.
More tabs, more feeds.
If a functional programming language requires a strict, unbreakable acquire, use, and release framework to prevent the system from crashing, what would an intentional acquire, use, and release framework look like for how we manage our own daily influx of information to prevent our own mental too many open files errors?
That is the real question.
Something to mull over the next time you find yourself with 50 tabs open in your browser, wondering why your system feels a little sluggish. Thank you so much for joining us on this deep dive.
It's been a pleasure unpacking this architecture with you. Until next time, keep exploring, keep building, and keep closing those files. Goodbye.